Good afternoon, ladies and gentlemen. Our project is the effects of microgravity on Shewanella Oneidensis.
My name is Esteban Fuentes,
My name is Ayomide Akintola.
and this is our project. Not in attendance are our co-principal investigator Abdul Adisham and our collaborator Umar Sheikh. Our teacher facilitator is Michael Bowling, and we attend Harmony Science Academy, Houston High in Houston, Texas.
Our inspiration for this project was that while my group members and I were doing our preliminary research on trying to find a project, we stumbled upon an article talking about how space debris was and could damage our satellites and spacecrafts. And as we were searching for a solution to the problem, we discovered S. Oneidensis, otherwise known as MR1.
Let's take a look at the facts. NASA currently estimates 21,000 man-made pieces of space debris larger than 10 centimeters. Now picture 21,000 metal softballs, which is about the size of 10 centimeters, orbiting Earth at speeds of over 17,000 miles per hour. In addition, there are over 500,000 more pieces smaller than 10 centimeters orbiting Earth. As a result, astronauts must sometimes delay work due to dangers of being hit by a piece of space debris. A recent example is the collision between a Russian spacecraft that was struck by a piece of space debris from a Chinese satellite not too long ago in 2013.
As you can see in this artist's depiction of the space debris, it gives us a little visual as to how much space debris inhabits our atmosphere.
So how can we reduce the amount of space debris in orbit?
We propose to send MR1 to the ISS to study its ability to consume metal in microgravity. MR1 is a bacterium which lives in both anaerobic and aerobic environments, which means it can live in environments with or without oxygen. This extraordinary microbe feeds on and thereby consumes both poisonous and non-poisonous metals such as iron, lead, aluminum, and uranium. This is a picture of colonies of MR1, as you can see.
Now for our experimental design, we wanted a simple design that could put MR1's ability to consume metal in a microgravity environment to the test. So for that, we came up with this. Our materials would include 4 milliliters of distilled water, 2.5 milliliters of MR1, and 2 grams of lead. Now we would position a clamp in between the tube provided to us by the NCE SSE, separating the tube into compartment A and compartment B. Now in compartment A, we would have the microbe MR1 with distilled water, and in compartment B, we would have the lead. Now, a lot of people ask us the question of why we chose distilled water. Now, we wanted a simple fluid that could easily disperse Shewanella oneidensis onto the lead. And another question is, why did we not use a fixative? Well, we wanted the microbe to come back alive on Earth so we could study its behavior if it reacted any different from the ground truth experiment. Analysis to this experiment, once it returns Earth, will determine the change in mass of the lead, as well as characterize any changes to the lead surface observable at microscopic level.
If we were to send MR1 into a microgravity environment, then the microbe's ability to consume metal should remain unaffected.
Though not selected for flight, our ground truth experiment is currently on delay due to funding, but we look forward to presenting our findings at the 2017 SSEP conference.
Special thanks to the following companies and organizations.
Any questions?
How long will you have the microbes exposed to the lead, and how fast do they reproduce?
We plan on having it 2 days after the arrival. We want it to get a little bit used to the microgravity environment, and then we plan on the astronaut unclamping it and allowing it for the remainder of the time to enact with the lead.
So my name is Aaron. I'm from the University of Maryland. So if the purported function of these bacteria would be to digest like space junk that's out there in space, how would you propose getting it, if it worked, if it were able to digest the metal in microgravity, how would you propose getting it to the 500,000 pieces of space junk that are orbiting out there?
Well, the thing is with this microbe, it easily, it's in pellets. It's like, well, we received it in small pellets and stuff like that. but we could probably, since it's orbiting at certain speeds, we're not really sure onto how we could do that. But later, if this functions, we could actually get more into thought and more science to figure that out.
Thank you.
Hi, my name is Marina Good. I'm from Princeton, Massachusetts. So do you know how long it takes for this bacteria to hit its lag phase? Because one concern with my experiment at first, it was rejected and then accepted after we revised, was that it would eat itself into starvation. So we introduced a growth inhibitor to prevent that. So do you have any idea what that's like with your microbe?
Could you repeat your question? I don't really.
So basically, like, how long does it take for that bacteria to hit the point where it begins to die because it's eaten too much of its nutrient or too much of what it needs to sustain itself?
The microbe was recently discovered not too long ago, and there's not so much information that we have. We had to base it upon trial and error. So we have an estimated time of maybe 10 days or so, but we're not completely sure.
Thank you.
Hi, my name is Yaniv from the University of Maryland. So do you know what the temperature tolerances of this organism is? Because you mentioned it's anaerobic, so it could grow without oxygen. But do you know if it can tolerate heat and cold and still grow?
Are you asking at what temperature it grows and starts to reproduce? Or?
What's the optimal temperature and what are the limits of what it can tolerate?
Well, we know that at the rate it begins to multiply is at 30 degrees Celsius. But to answer your question, I'm not really sure.
Thank you.
Thank you, guys.